back in the section 3.5, talking about the what we call the complex conjugate theorem. I think actually you took a textbook called the conjugate zero theorem, something like that. Basically, what it says, if you have a polynomial in which there is a zero in it that is complex of the form a plus bi, okay, then its conjugate is going to show up as well. And my hopes are that you guys understand why. Think about what we've done in the past. Think about all the algebra you've done in Algebra 1, Algebra 2, that kind of stuff. If I have a, let's see if I can think of one. Let's just do this. I know for certain now it's because it shows up here in this problem. If I have that parabola, okay, it does not factor using products and sums. Okay, it does not work real nice with any other idea other than the quadratic formula, right? Okay. When I do the quadratic formula, I do opposite of b plus or minus b squared minus 4ac, right? All over 2a. That plus or minus, guys, what does that create for us? So 6 plus or minus. Okay, now it's going to be negative 4 underneath here, correct? All over 2. If I start reducing 4, negative 4 come out as an I, right? Comes out as a 2i. Is that all right with everybody? And then I've got 2. And I start reducing that, then I get 3 plus or minus I, correct? Follow that plus or minus all the way back through into our quadratic formula. What are 3 plus I and 3 minus I in comparison to one another? Conjugate. Okay? So, the idea that if I have 3 plus I as a 0, okay, because it came from a quadratic factor, then 3 minus I is also 0 because it came from the exact same quadratic factor. Because of that, or quadratic, yes, factors. Because of the fact that when we work with our quadratic formula, it's a plus or minus there, right? We took the square root. So that's kind of the idea behind why we know that if 3 minus I is a 0, okay, and it's in the a plus bi form, that's in terms of right now, then its conjugate, 3 plus I, is also a 0. Okay? Does that make sense then that I should have a degree 3 p of x? The problem says find p of x of degree 3, but they only gave you 2 pieces of information, right? Well, knowing my complex conjugate theorem, I now know actually all 3 parts. Okay? What I want you guys to understand, the way we're going to view this, is that my a plus bi, to determine a conjugate, it has to be in that form. Okay? So if I had something like 2i plus 3, its conjugate, we want to rewrite this as 3 plus 2i, and now its conjugate is 3 minus 2i. Does that make sense? Okay? Keep that I at the back. The way we do, the way we define what those conjugates are. Okay? All right, so if I want to find this polynomial, p of x is going to have x minus something, x minus something else, x minus something else, right? That's what degree 3 tells me, is that I'm going to have 3 factors. One of those factors is 1/2. The other factor, now, 3 minus I, that's a quantity. It's 2 objects. Okay? You got to put that in parentheses. 3 minus I. And this one will be 3 plus I. Okay? Now, most of the time, they want us to multiply this out. And when they say that it has integer coefficients, they're telling you you have to multiply this out. Okay? Because when I look at that, I don't know what my coefficients are for my x to the third, x squared, x to the first, and so forth. Is that all right? We have to multiply this out. Now, here's the thing. You can multiply, because it's multiplication, you can multiply any of that stuff out you want. You can grab any two of those factors and multiply them out. My hopes are you recognize which ones are convenient to multiply. Okay? I would use the conjugates together. Now, I'm going to show you two techniques. Doing kind of brute force foiling here takes some effort and time and thought, and just really paying attention to detail in regards to your signs. It's doable. I think you'll have the capacity to do it. But I'm going to show you then the nice thing about having a little bit of algebra skill, a little bit of understanding of what that is actually saying to us that can kind of almost instantaneously give us that problem. Okay? So if I do first times first, so the first times first, right? So x times x gives me x squared. Okay? Now we do outside times outside. Okay? Now this is a quantity, right? And it's negative, correct? So this is the way I'm going to write. I'm going to write negative. Now I've multiplied the outside term x times the outside term of 3 plus I. This is the nasty part of it, is getting that sign, because this was negative, sorry, this was positive x, and this quantity is negative. Okay? So I'm just going to write the implied multiplication. I'm not going to do that yet. Now I'm going to do inside times inside. So that would be that one times that one. So it's really the same idea. It's a negative 3 minus I times an x. So we have negative x and then 3 minus I. And now we'll do last times last. Now last times last is a negative times a negative, so it becomes positive. And then it's 3 minus I, 3 plus I. Okay? That's the messy part of multiplying those two things. Okay? But still a FOIL process. If we just pay attention to 3 minus I is 3 plus I is just one object. Does that make sense? With the front of zero. Okay? If you're a person that doesn't like that, okay, can I do something like this? We see this a little bit before, and I didn't talk about this the last class, but let's say I don't like that multiplication, gets messy. Let's say I go and write 3 minus I, let that be U. And let's 3 plus I, let that be W. Then what does this look like? X minus U, X minus W, does that make sense? Could I then go X squared minus UX, be then minus what, XW, and then minus U times W. And now think about what this would look like if I put U in. U was 3 minus I. Did I give you that right there? If I put W back in, W was 3 plus I, gives me this term. Okay? And then U times W would be those two things multiplied together, which give me the things in red. Right? You could do that if that makes more sense to you. I'm going to show you even a better approach here in a moment after we get done with this way. I'm going to distribute my negative x's, so negative 3x minus xi minus 3x plus xi. And now I get to the red stuff. The red stuff, what are those two things compared to one another? Conjugates. So do I need to worry about OI? Nope. So 3 times 3 is 9. And then negative I times I gives me negative I squared, right? But negative I squared is the same thing as 1. Right? So I squared becomes negative 1, right? But negative I squared becomes minus negative 1. So we should have then a total of 10 there with that red stuff, right? Okay. What happens here with my negative xi and my positive xi? They cancel out. And that should happen every single time. Because think about what we're doing here, guys. We're taking, I already showed you the quadratic formula, that x squared minus 6x plus 10 is going to give me 3 minus I and 3 plus I. Okay, so these zeros came from a quadratic function. Is it quadratic function or quadratic factor, I guess? Maybe the best way of talking about it. Does it ever have I in it? And ax squared plus bx plus c, is there an I term in there? No, so they should cancel out, okay? If they don't, maybe we've done something wrong, okay? And we would maybe want to go back and make sure that this stuff is written correctly and multiplied out correctly. So it gives me x squared minus 6x plus 10, right? That's a blue factor. Now I got my x minus a half still out there. So now what do I have to do with that x minus a half? So I have to distribute that through. Okay. So x times x squared gives me x cubed. X times negative 6x gives me negative 6x squared. X times 10 gives me 10x. Now my negative 1/2, so negative 1/2 x squared. Negative 1/2 times negative 6 gives me 3x. Negative 1/2 times 10 gives me negative 5. Okay. So now we're going to combine like terms there, and we're going to have x cubed minus, so negative 6x and negative 1/2 gives me negative 13/2 x squared plus then 13x and minus 5. And my question is, have we answered the overall problem? Have we created a P of x that models what they ask? Heads bobbing up and down. I can see more heads bobbing left and right. Integer coefficients, right? Is this an integer right here? No. So what do I need to do to this polynomial? Okay, multiply by what? Okay, 2 would be fine. Multiply by 4. Multiply by 6. As long as I multiply by a even number, and it could be positive, it could be negative as well. I would probably venture to say I would probably want a positive one. It's going to make things a little bit easier here. But multiplying everything by 2 would give that thing there, right? Okay. Now that's the P of x they're looking for. Here's the thing, guys. If I write in a test, my test, sorry. If I were to write in a test this question, I think about the results that I could have and how I'd have to grade that. Should I have, if I've got 36 students, could I have potentially 36 different answers down at the bottom if I left the directions that way? So that's kind of how sometimes when you read a problem, you're like, well, this one doesn't match up to what we've done in the past because there's more words in the description, more criteria, and so that we get everybody kind of narrowed in on one specific function that we can then analyze and grade correctly the same way. So what I would do on a test, because you can still have, you multiply by 4, 6, 8, whatever, goes by negative. So what I would probably do is I would say find a final P of x of degree 3 that has the smallest possible integer coefficients. Does that make sense? When I say smallest possible, it means you have to multiply by 2, correct? Okay. Now some people say, well, I can multiply by 2 or negative 2. Okay. So then what I would do is I would say smallest possible integer coefficients where your leading term is positive. Does that then force you to have a 2 there? Okay. So those are little things that are added to problems so that we can kind of all get down to the same result. Now, that was kind of a pain in the butt. Hopefully you agree that was a pain in the butt doing that multiplication right here with the x minus 3i and x plus 3i stuff, or x minus 3 minus I, x minus 3 plus I. Here's the benefit of knowing a little bit of algebra. What this says is I've got x minus this quantity, right? Is that the same thing as x minus 3 plus I? I distribute that negative through. Okay. Is this one over here the same thing as x minus 3 minus I for the same reason? Let's do this then. Let's take Southeast side. All right, so we got our plus I in the back, we got our minus I in the back. Can I take this x minus 3 and that x minus 3, and just reposition my parentheses. Because what is x? What's x representing? A what? Say again? Careful. We're going to use the 0, 5 property to find out what the 0 is, what value of x makes a 0. But isn't x just any number that we want it to be? X is just a variable, right? X can be anything. So let's just say x was 10. Would that be 7 plus I and 7 minus I? If x was 13, would that be 10 plus I, 10 minus I? No matter what x is here, that red stuff goes to just a numerical value, right? And when I do that, does that product become a product of conjugate? So what's nice about conjugate? O and I cancel out, right? So the O and I, the mess up here, I think, that people have is getting the signs right in between here when we leave it as this multiplication without doing the U substitution, W substitution. If I do it this way, x minus 3 times x minus 3 looks like that, doesn't it? I know O and I are going to cancel out because these are conjugates. What's I times negative I? Negative I squared, right? And negative I squared turns into plus 1, right? So what's x minus 3 squared? Well, x squared minus 6x plus 9 plus in my 1 there. Does that give me the same thing a little bit quicker? All right. So that's the benefit. I think, obviously in Algebra 1, 2, 3, we do all this stuff. We're analyzing polynomials and that kind of thing. But I think the algebra, the most important type of algebra, part of algebra, is that kind of stuff. Because what that allows me to do in calculus, it allows me to do the problem 2 or 3 times quicker than my neighbors. Okay, and I become more efficient, more productive. Okay, so I think those are little things that we want to kind of store. How often are we going to use it? I don't know. Maybe we use that once or twice a year. But it's a nice thing to have. Okay, and we're just using that now with these complex numbers, but maybe down the road it shows up somewhere else that would be useful. Okay. So reorganizing things, using my associative property and that type of thing, understanding what variables are, is a very convenient thing for us. Okay? Sadie?
When we first multiplied the equation, I thought you said you can't calculate the number in terms of TX. So you have to consider.
Say it again?
When we multiplied the equation, I thought you said we can't calculate the number in terms of.
We're just multiplying the right-hand side. Because we don't know that. So we got P of x is equal to something, right? And it has some rational coefficient. We just want to do something. That's not our final result. We want to make sure that our final result has the same zeros that that thing has, but has positive, or not positive, integer coefficients. So I mean, we just multiply the right hand side by 2. We don't multiply the left hand side. Just leave that one alone. So now, guys, what I like to do, obviously, I'm always with jumping back and forth between GeoGebra. Use it, okay? Use this thing to help you make sure you've done things correctly. So there's a lot of work here. I would hate for you to go through all this work and come up short, okay? So I'm going to go ahead and type in that function we had. It was 2x to the third. Was it minus 13x squared? Thank you. All right, so I just want to look at this. I want to make sure, does it match the criteria provided? We had one real 0, right? 1 0 that came from the real number line, and it was 1/2. Or, yeah, 1/2. Is that what's happening right here in my picture? Okay, it looks like if I zoomed in on there, you can see that's 1/2. The other zeros were non-real zeros. Well, non-real zeros, will they graph on the XY plane? No. Okay, so this kind of makes sense. Okay, we had 3 zeros, we got 3 factors, we have a cubic. I'm going to go one step further because GeoGebra has this capacity. UTI 384, I don't know if Desmos has this. If I type in complex roots, I've got to follow the notation. It's got to be complex, capital C, root, capital R. And now I just type in my function. Now I need to type in 2x cubed minus 13x squared, so forth, or just type in f of x. And hit enter. Look what it puts back to me. 1/2 plus 0i, that's just 1/2, right? 3 minus I, 3 plus I, is that what we started with? Yeah, okay. Now you see down there on the graph as well that they actually graph those points D1, D2, and D3. What they're doing here is just kind of strange, I think. The green graph is your XY plane, right? That makes sense? Okay. They're taking like a transparency paper. Okay, you guys know what I'm talking about when I say transparency paper? Okay. And they're putting that on top of the XY plane. Okay. And on that transparency paper, they have the complex plane, which the complex plane has the exact same structure that the real plane has. It has an x-axis or a horizontal axis. We call it our real axis. It's the A value. And it has a imaginary axis, which is what would kind of refer to your Y values or your BI values. So you're seeing really two planes on top of one another. Does that make sense? We will talk more about the complex plane and introduce it later on, but it's basically this. If I've got A, and this is my imaginary axis, okay? If I wanted to graph 3 minus I go over 3 on the A-axis and down 1 on the I-axis. Does that make sense? And that's how I graph complex numbers, okay? So they're doing that kind of over the top of the XY axis. All right, so let's do one more of these. I want to find a polynomial of least degree that has -2 plus I and I as 0. -2 plus I and I as 0. Again, the moment that you start using the conjugate theorem, you have to understand that your zeros that they provide you need to be the A plus BI format. If you remember back to the theorem we said yesterday, let's look at this. Here it says, I guess the theorem doesn't say it the way I wanted it, so I was hoping it would say it. Because they've introduced D, complex number D. But if D is being defined as A plus BI, that kind of makes sense? Okay? Then its conjugate is A minus BI. Okay? So that we want to make sure that we understand that's the way we define our conjugates. And the reason I say that is at some point I might get tricky with you, and I might write that your 0 is I minus 2. Well, I plus 2 is not the conjugate. Does that make sense? Okay? Or the complex conjugate, because it doesn't have the relationship that we want. Okay? So what I have, -2 plus I? We want to write it that way. Okay? So now, finding P of X. What's the degree of this thing going to be? It's going to be 4th degree. Okay? Because you have X minus -2 plus I, and you have X minus its conjugate, right? Its conjugate is -2 minus I. Remember, conjugate, the only thing that changes is a sign right there. Okay? In the past, I get people to change all the signs. Don't do that. You change the one that's connecting them. So that's the first 2 zeros. Now I'm going to have X. Now, you usually don't write this, but 0 plus I is another way of saying I, right? What would that conjugate be? Yeah, 0 minus I, right? Which would just be minus I. So we have X plus I and X minus I. We're just going to FOIL that out. Now, once I FOIL this out, it does not say that we have to have certain coefficients or anything like that. It doesn't say find a particular A value. I could give you maybe another point that's on this curve so we can find A if we needed to. But we're just going to FOIL it out and just kind of basically come up with our general format of any one of these polynomials that have these zeros. Okay? With doing these two, I'm going to go to the technique that I finished with on the last one. I'm going to distribute the negative through. So it becomes plus 2 minus I. And it becomes x plus 2 plus I. And I like to group those two. I should probably write, depending on your organization skills here and doing these problems. A lot of times what I'll do, I'll just go to the side and I'll multiply these out, get what that product is, go to the side and multiply these out, get that product, and then come back together and write them down here, okay? Your choice on how you're going to want to do that. If I multiply these two that are black here together, that's going to be first times first would be x plus 2 squared, right? Now the conjugates, okay, the way we've organized these x plus 2s and these are parentheses, those are conjugates. So I don't need to worry about O and I can do last times last. So it gives me negative I squared, right? Okay. Come back and do that again, or do the simplification there. If I come over here to this red stuff, x plus I times x minus I, times this again, right? X squared minus I squared, right? So this is going to provide, we're going to FOIL that out. What is it? X squared plus 4x plus 4. Okay. Minus I squared, so that's minus a negative 1. Minus a negative 1 becomes plus 1, right? So eventually all that stuff in black is going to turn to 4x plus 5. X squared plus 4x plus 5. The red stuff, what's the red stuff going to turn into? X squared plus 1. All right, so we've got that garbage now. And what we got to do with that? We're going to multiply that out one more time, right? So my hopes are you start to see that, and I can't ask too many questions on a test or quiz, right? If I start FOILing that, or I guess it's not FOIling, but distributing that through, I'll take the x squared through everything. It gives me x squared times x squared, which is x to the 4th. X squared times 1 will give me x squared. 4x times x squared gives me 4x cubed. 4x times 1 gives me 4x. 5 times x squared gives me 5x squared. And then 5 times 1 gives me 5. Go ahead and combine all your like terms. So our final p of x that we're looking for here, x to the 4th plus 4x cubed plus 6x squared plus 4x plus 5, right? Now I want to analyze. I want to look at this real quick in a graph. Okay, so stay with me. I go x to the 4th plus 4x cubed plus 6x squared plus 4x plus 5. Why would that thing be hard? If I started you off with the problem, with a polynomial x to the 4th plus 4x cubed, why would that be hard for us to grasp? What is the number one thing that we're looking for in this section, this chapter so far, to graph things? The zeros, right? It doesn't have any real zeros. So we could graph the end behavior, we could graph the y-intercept. That's really all we get, right? Okay? This type of function, this polynomial, is where our calculus would kind of take over. Okay? When we graph that one, we'd have to use what we call the first derivative and second derivative test to help us get a better kind of grip on what that thing looks like. Okay? But what I like about GeoGebra, again, guys, once you have it, we've done a lot of work. Let's see if that work is right. Type in complex root of my polynomial. And does it give me the zeros that we started with? Yeah, if you did something wrong, it's not going to give those back. Okay? So hopefully you're maybe using that to protect yourself on your homework. Now, unless you use it, when we get to our test, you can use GeoGebra on your test. Have a great day. Thank you.